thank you all for being here and for giving me the chance to talk to you. I know some of you, but certainly not all of you. So nice to meet you virtually. What I'm going to talk about here is so I'm going to do kind of a bottom-up derivation of what science networks are and what they are in the context of the internet more generally, and then what that means for us who, those of us who are trying to make multi-site science workflows work in a way that is productive for our scientific colleagues. Um, so, um, so what is a science network, right? I mean, you can see a picture of one behind my head. Um, but when we do things in a lot of workflow contexts, right? We talk to a cloud or we call an API somewhere, we stream stuff, whatever, right? This happens, air quotes, via the network. Okay, so what does that actually mean? Right? That means an application gets a socket and data goes in packets to the other side, right? Wherever the other side is. Um, and how that happens, the details of that aren't always familiar to people who are working on the software stacks that support science. Now, I apologize. I know some of you know some of this already. And it may be that some of you don't know some of the details. What I'm going to try and do is provide a common foundation that we can all sort of build up from for the rest of the talk, right? So, we all know what an ISP is, right? I mean, I'm at home at the moment. I'm lucky enough to have fiber to my house. So that's my local residential broadband ISP provides that. If I want to watch a movie, I can do that. My phone's connected to an ISP over, via a cell provider instead of via, fiber at my home, right? But this kind of thing is what most people think of when they think of air quotes, right? The internet, right? Science networks are the analog of that, right? They interconnect scientific sites, national laboratories, facilities, supercomputer centers, telescopes on mountaintops, tokamaks, right? An electron microscope someplace, the Large Hadron Collider, whatever, right? And they use the same protocols as the rest of the internet, right? So it's all forwarding IP packets. Most of the data transferred is over TCP, except for the stuff that's now using QUIC, though that's slower, even though it's over UDP, right? And science networks are also connected to the rest of the internet, right? They use the same internetwork signaling, BGP, as the rest of the internet does, right? They're just a little bit different than what we can think of as the commodity internet, and I'll go through why. Right? So what is the internet as a whole, right? It's a whole bunch of individual networks that are connected together for various reasons. Each of the individual networks that make up the internet are built, deployed, operated by whomever did that, right? For their own selfish reasons, right? So Google's built its network for its own reasons. The military has a network, actually several of them, that they run for their own reasons, right? A large industrial company like Ford, right? What do? They're not in the internet business. They make cars. Okay, but they have their own network that they build and operate for their own selfish reasons. The Department of Energy Office of Science has a network that is built and operated for its own reasons. That's YesNet. Hi. AT&T has a network that they build and operate for their own reasons. They provide cell phone service as well as ISP type transit, right? So there's a whole bunch of these all scattered throughout the world, each built for their own reasons and interconnected to a portion of the other networks of the internet for their own reasons. Right, and people talk about network effects, right? Networks are more valuable when they're connected to each other in this larger network that we call the internet. But why a particular network connects to another is selfish, right? It's for the reasons that the person who built that network need, right? It's outcome driven, right? If I have a network and you have a network, I want to connect to you because I will see value from doing that, right? And that's how the interconnection architecture of the internet comes to be and changes over time. Everybody's doing what they're doing for their own reasons, right? And so here's a trivial cartoon describing some of those things, right? And this is radically simplified, but it's intended to show some of the different kinds of relationships that exist. So if you're Google, right, what do, right? You have a search application that's driven out of warehouse scale data centers, right? You have YouTube content served out of warehouse scale data centers, some enterprise apps, right? Gmail, Google Docs, things like that. Those are not useful to your customer base unless they can get to the data centers where all that stuff is. And so people either need to connect directly to Google's network or to somebody who will get them there, right? And so that's your ISP there to the right of Google. So there's a whole bunch of folks who connect to an ISP, right? So that's, like you know, get through my phone or through my home broadband ISP, right? I don't have a connection to Google in my house. I have a connection to Sonic in my house. Sonic gets me to Google, maybe through an intermediary I haven't checked. Right. So all of this is fractal and recursive, right? But now you look at the blue tinted ones, right? These are separate networks operated for science support, right? And they're their own networks engineered in their own ways, and they connect to other things that make sense. So ESNet's connected to Internet 2. Why? Internet 2 gets us to the U.S. university complex to first order. We're connected to some regionals, but if we are not connected to a regional, Internet 2 is, so that's how we get there. Same is true for Europe down there at the bottom right. So anyway, this goes on and on and on and on and on. And if you want the super crazy diagram of what it actually looks like, go follow that link on CADA. They do some amazing internet mapping stuff. And the maps are just amazing. But the point of all of this is each of these networks exists for their own selfish reasons, and those reasons vary depending on why someone built the thing. Nothing is set in stone. The lines are a little bit blurry, right? So AT&T, for example, serves as both an ISP and as a cell phone provider, right? For example, but that's okay. The thing that's important there is that why the thing is built affects how it's built. And so not all networks are engineered in the same way. Some are better or worse at supporting different use models. And in particular, science networks have a different traffic profile and a different usage model than the commercial networks do. So here's ESNet, right? We're not actually an ISP, even though if you're a laboratory and you want to do a Google search, it'll still traverse us because we support that protocol stack too. That's not the reason we exist. The reason we exist is as a DOE user facility, we advance the mission, the science mission of the DOE Office of Science and the National Laboratory Complex. And so there's a set of things that ESNet builds and provides as part of our network that are optimized for science, not optimized to support a billion cell phones, right? Which a network like AT&T is. So a billion cell phones is a primary customer for AT&T, right? Cell phone traffic is an incidental customer for ESNet. So you can think of us as the data circulatory system for the Office of Science for the National Laboratory Complex, right? And so our job is to provide reliable, yes, and high performance connectivity between the labs and also to the rest of the science internet and the general internet and the commercial cloud. And so what you get then is the ability to easily exchange data no matter where the computing, the data source, the person is. And so the way we think of ourselves is as removing the constraints of geography from scientific progress, right? And in doing so, accelerates science. So an example of something that takes advantage of this is the Large Hadron Collider. So in the top left there's a map of the LHC laid out on France and Switzerland. All the lines that are there are tunnels that look like that middle thing. CMS, Atlas, LHCb, and Alice are big detectors. The upper right there is, I'm pretty sure, the CMS detector. Inside, they collide protons together. There's an example of the collision, and turns out they won a Nobel for that. Not bad, right? Not bad at all, folks. But in order to do that, right? So that's where the accelerator is. The global science internet, of which ESNet is a part, facilitated the computing and data analysis that led to that Nobel Prize. Right, so ESNet is the primary carrier of LHC data in the United States because the two LHC tier ones for CMS and Atlas are at national labs and directly connected to us. But there's a whole bunch of science network providers all over the world that provide connectivity for this. And that spaghetti diagram in the lower right is maintained by my friend and colleague Bill Johnston, illustrating all the relationships that go into carrying LHC data. Okay, so another example is the Vera Rubin Observatory, high up on a mountain, Cerro Pachon in Chile, right? And so the data comes off of that thing, right? It's the world's largest digital camera, 3.2 gigapixels. It's pretty amazing. The data comes down off the mountain, traverses a bunch of science networks, ends up at Slack for prompt analysis and alert generation, and later for the generation of data products for use downstream by the astronomy community, right? So this includes not just the workflow there on the left, right, which is the raw data coming down every night. But then there's a set of data products that get released. A bunch of those will end up being analyzed by Jupyter notebooks in the cloud. So there's a cloud networking component to this as well. And all of this has to work in a performant way all the time, right? So these are just examples. There are a lot more experiments, a lot more collaborations, a lot more facilities involved in this. And I've listed some of them there, right? Light sources, everything in the Fusion Research Program, genomics, computing centers, whatever. And essentially every one of these today uses networking, either to connect to a remote thing, to transfer data around, or in the interest of this community, right, to run multi-facility workflows to get more out of the science than one could get out of one facility alone. And so, okay, well, we interconnect the entire DOE facilities complex. So there's a whole bunch of them. ESNet's down there in the lower left. And this talk would not be complete without at least one shout out to the IRI program, which I know several of you here are very familiar with and are actively working on, which is great. So the intent here is to make it easy and routine for multi-facility workflows to take advantage of everything that the set of, all of these facilities, right, to first order have to offer. One significant way this is done is by connecting the computing centers to experiment facilities, but that's not all of it. Some of it's computing center to computing center. There's a bunch of different. Some of it's connected to the cloud, as I mentioned previously. There's a bunch of this, but there is in fact a formal program around this that's under development now, and we've already seen some successes. So, all right, so what's a multi-facility workflow then? All right, so it's easy to say it's a workflow involving more than one facility. Well, okay, what's that actually mean? So there's a bunch of different components that all happen via the network. Some of it's moving data around, some of it's orchestrating stuff, results display, orchestration of computing and analysis tasks. Some people just worry about the APIs, right? So, okay, so we want to do this. What has to be done at the network layer and at the site sort of systems deployment layer to enable all of this stuff? So it's easy, if you're naive about this, and everyone here is actually more sophisticated than this, right? But if you're naive about this, you say, okay, well, how does a human do it? And I'll just bot that. And I have certainly written plenty of code to bot a command line interface before in my career. I expect several of you have done the same thing. It's very painful. And it doesn't actually get you to where you need to go in the long term anyway. So machine consumable interfaces are much better for machines than human consumable interfaces. Uh, However, a machine can't reason about what happens when something behaves in a way that it's not supposed to. I mean, sometimes you can, right? A hard failure, okay, fine. If something fails hard, it's relatively easy to build logic to deal with that, right? You raise an exception, you can try again. There's depending on the exception type, you might do something else. Okay. Soft failures, though, typically require a human to reason about them, right? So what happens if performance just drops by a factor of 10? Everything still works, it just works badly. Now what do I do? Okay. And so if we want multi-facility workflows to be scientifically productive, then the science community that uses all of these things has to be able to trust that they'll work well all the time. Because otherwise, they can't plan their life and they can't trust the thing. And what they'll do instead is they'll go build their own stuff and operate it poorly, but at least they'll understand it and they'll be able to deal with it when it doesn't perform as it should, right? And so, if we want to be successful in building things that are adopted by the science community, it has to work all the time and it has to perform well and perform well consistently so that they can trust that it works and organize their life around its behavior. And so the wide area interface to a lot of this sort of stuff is something called the Science DMZ. I've got a link there. And I'm not going to go into the whole Science DMZ thing now. If anybody wants to talk about the Science DMZ, I'm happy to do so ad nauseum. I'm not going to do that here. The point of the exercise is this is a place where wide area facing services can be deployed in a way that is both performant and safe to operate. And by putting those things there and making sure that they work there, you don't inherit all the complexity of the rest of the enterprise network when you're trying to deploy these things. Now, here's the thing, though, right? This is a case where limitations are actually enabling technology. So the thing that's important is in the Science DMZ, we only put things that can be secured with stateless firewalls because that's how we can ensure consistent performance. And what that means is that they can't be complicated, right? So you don't put a database-driven web services application in the Science DMZ. Why? Because you can't secure a database-driven web services application without protocol analysis and in many cases deep packet inspection. You can't do that stuff in the stateless firewall. It's a bad match. Don't put it there. And in general, you don't need tens of gigabits or hundreds of gigabits of performance in data throughput for a database-driven web services application, right? That might be the orchestrator, but that's not necessarily the data path. And so you put the data path in the performant enclave, and you can put the control channel or whatever someplace else. So in terms of like application design, workflow design, the separation of control signaling and data transfer is actually really, really valuable, right? If you make the assumption that they'll take the same path or that they must take the same path, then you're limited in the performance engineering that you can do, and therefore in the degree to which you can take advantage of all the capabilities that the science internet has, because you're stuck with low performing security technologies because everything's too complicated. If you can separate the data piece out from the control channel and orchestration, then each can be optimized and each can be secured in a way that's appropriate to each component of the workflow. So that's basically the frame for this whole thing, right? There's a separate science, air quotes, science internet, basically, that has a set of capabilities that are not available in the commercial internet, and has performance not available in the commercial internet. I didn't put the graphics in this deck, but it's happened twice now. People have gone and tried to do run high performance data flows across the commercial internet. Once they hit about a gigabit a second, it's assumed to be a denial of service attack, and the flow dies. It takes about 1 second to do that. Whereas in our world, a 50 gigabit data transfer is ho hum, whatever, normal business, bring me another, right? And so that's one example where the networks themselves are designed to support science in our world and not in the commercial world. And then, but in order to use all of that infrastructure effectively, right, the site architecture needs to be right, and the workflow design needs to be right. So I'm going to leave that there, right? And again, this is about removing the constraints of geography from the work that our science colleagues do to make the world a better place for all of us to live in. So thank you very much.